Okay, thank you so much, Bharti, and thank you for inviting me. And this has been a very nice visit in a very lovely campus. So, today I'll talk about this work that I've been doing for about a year. We've been working on this and and a couple of other projects actually related to this. And with Shobhit Ghosh, who's a research associate, working with me on this. And so all of these projects are part of the Google Research project that I'm working on, and very generously funded by Google Research India. And let me just get started on this. Just click the mouse once it starts. Okay. Yeah. So the fundamental idea behind this paper is looking at something called intergenerational transmission of health. And if you've been following the literature, right now there's an influx of work happening that looks at intergenerational mobility. Okay? Basically asking a fundamental question that is each generation better off than the previous generation? And breaking down this idea of what do we mean by better off? Okay, is it just income? Is it wealth? Is it education? Is it health? There are many, many different angles to which you can look at this. And so tied closely to that idea of intergenerational mobility is the idea of intergenerational transmission of health, which basically means like how much of our health do we actually inherit from our parents. And if you think of health as an asset, there's a stock and there's a flow. You can think of there's some part of health that we inherit from our parents, and then over the course of our lifetime, we contribute to it. Some of it depletes, some of it, we make investments in our health so it gets better and so on. And so there are many ways of measuring what is this intergenerational transmission of health. So, why is this so important to look at? Because this is one of the channels through which health inequalities persist across the population. How much we inherit from our parents, how healthy we are at the start of our life, actually tells us a lot about how healthy we're going to be for the rest of our lives. And this has been sort of, Sonia Malhotra has several papers on this where she looks at cross-country comparisons of intergenerational transmission of health. And more recently, a little bit earlier work, Erickson suggests that the health status alone actually accounts for about a third of the magnitude of intergenerational transmission of parents and child's income. So it links very closely with our idea of human capital, right? Human capital being both health and education. And if we just look at the health part alone, that alone contributes to about a third of the intergenerational transmission between parent and child's income. So, this idea of intergenerational health, it's rooted in the ideas of intergenerational mobility and distributive justice. Okay? So in my paper, I actually take this and then dig into this a little bit deeper. Okay? Which is, I'm saying that the extent of intergenerational transmission of health itself depends on our circumstances. Okay? And what do I mean by circumstances? Circumstances are those characteristics over which individuals have very little control. So, for example, the amount of health that you can inherit at birth can be dependent on your parents' income. You have no control over that. It could be where you are born, the zip code. So if you're following Grad Chetty's work at Harvard, he does a lot of work where he looks at the extent of zip code, how much the zip code where you're born actually affects your adult income and so on. And then there's a whole lot of other characteristics. So I'll talk about what I include as circumstances, but they will all be characteristics over which individuals have very little control in their lives. So, for example, from prior literature, we know that children are more likely to bear the effects of poor maternal health. So, if your mother is sick, you are more likely to bear the effects of poor maternal health if you are born in adverse socioeconomic conditions. Okay, so there are these other mediating factors, okay, which affect how much of our parents' good health or bad health we we get as when we are born.
This part you are talking about the initial condition. At birth.
At birth.
This is the endowment that you get.
Yes, at birth.
Which is quite different from what comes later. Right?
It's very
That is the main idea of your study, right?
Yeah, I am only looking at intergenerational transmission at birth.
Okay. At birth, you are looking at that.
Yes. And of course, now as we so there are two aspects to this. First is how much our parents' circumstances affect how much we get at birth. The second is when we know that most developing countries have a whole host of these antenatal care, different types of antenatal care that is equivalent that mothers can take advantage of. But access to those variables, okay, access to different kinds of antenatal care also depend on maternal circumstances, right? So someone who is in a very rural or remote area could not get access. Perhaps it's harder to get access to, say, vaccines or proper checkups compared to someone who's in a city. So there is a lot of interlinkages between our circumstances and everything else. Starting from how much of health we start with at the beginning of life, as well as how much access to healthcare that we are able to get. So, this is what we are going to sort of parse and use machine learning very strategically to do this. I can take questions as we go.
Not very clear research questions. Circumstances, when you define intergenerational health transmission, circumstances are technically exactly what you define, exactly how you define intergenerational transmission.
No, so I'm going to specifically say intergenerational transmission is going to be a parameter in the model. It's going to be something we call elasticity of transmission. And circumstances are going to be the factors that affect that elasticity. Okay. So it's like saying how much of my mother's health am I inheriting? Okay. Of course, it's not precisely that. We will use proxies because these things are very hard to measure. So, for example, one proxy that I use in the literature is used a lot is birth weight. Okay. And so it's like saying, is there an elasticity of birth weight? That would be that extent is the transmission. Okay. And then everything else, like whether they're getting care, whether income level, household size, all of these are the circumstances.
So, for instance, one of the parameters of health is very widely agreed to in the medical literature and all that. But would be, let us say, the height of the child as the child goes up or whatever that is called. But that can change with the circumstances of your, what you were getting. I mean, irrespective of the maternal conditions at birth and the neighborhood and all that.
Yeah.
You get.
So in my model, I'm only looking at birth, where the height of the child doesn't get matter.
No, so
that comes much later.
You're not considering what happens after.
No. I'm not looking at the rest of the life.
Okay.
It's maternal circumstances, their effect on health at birth. I'm only going to focus on birth.
Okay, only the initial endowment.
Initial endowment.
Right.
Okay. So, I'll briefly talk about prior work because it's important to understand how machine learning actually helps us take this forward. So, prior work essentially, like not going into each of the papers, but we have established the importance of circumstances on intergenerational transmission of health. Okay? So, for example, I started with Sonia Balotra's work. She did this cross-country comparison and looked at some broad socioeconomic characteristics. Okay? And what all of these papers tell us is that socioeconomic characteristics are important. Okay? There are cross-country studies from the United States, Vietnam, Philippines, China, India. And then they tell us that these are this transmission, this extent of the transmission is heavily influenced by household income and wealth. And there are considerable non-linearities in this relationship. So put the word non-linearities in bold because that will exactly tell you where machine learning helps. Okay. The short version of the paper is we are going to use a machine learning algorithm to exactly characterize the extent of the non. So like, Janet Curie and Enrico Moretti have seen that it goes down to the level of zip code. So that's the level of nonlinearity we have. And then there's,
In most of the papers that you talk about over here, have they really used AI approaches in terms of looking at nonlinearity?
No. So all they say is there is nonlinearity, and the way they do it is they introduce one or two interaction terms, which is the traditional way in which a parametric way of looking at it. And how do they say that these socioeconomic characteristics are important? When you interact any socioeconomic characteristics with that term, it turns out to be statistically significant. So that's the traditional way of doing this. And then one small, curious sort of result that stands out in the literature is that this extent of transmission appears to be stronger for boys than girls. Okay? And I'll show that I do find some evidence of that in my paper as well. It's not as strong, but there is some evidence of that as well. Okay, so what is this paper? Okay, and as I said, it literally picks up where the previous literature leaves off. So I'm saying that the previous literature has said that these socioeconomic characteristics are very important. And I actually sort of identify and characterize different circumstance profiles, okay, which have varying coefficients of intergenerational transmission. So I'm exactly going to give you different types of individuals who have these varying extents of transmission of health.
The difference between boys and girls, that's a result for India or Japan?
This is for India.
So it means that the mother and the child sex preference is very more when she knows that canon does that work.
It's possible, but it's hard to test for mechanism here because we are just looking at we are just documenting a result here, right? That's definitely a plausible channel. So in order to test this, you have to find some exogenous variation and find to the causal, take it to the causal loop. But I'll show that there's some role that antenatal policies also play, but sex preference isn't something I model here. Okay, so yeah, so we are going to characterize these circumstance profiles using a machine learning literature, machine learning algorithm. And here I'm going to use inference-based machine learning tool, partitioning technique. So if you are a little bit familiar with the machine learning literature, you would know that it has this reputation of doing mostly prediction. Okay. Any familiarity with machine learning? Any? Yes. What are you familiar with?
So you think I work on it. So in general, I create predictive algorithms, the highest frequencies, and other than that,
okay. So if you know XGBoost, you know what a decision tree is. Okay. So I'll talk about this. The first generation machine learning algorithms. So when I say first generation, because the literature has moved on from there a long time ago, they were all geared towards good prediction. Okay. Now here I take one of those algorithms whose job is to do partitioning of the data, and then I break it down, and I'm using someone else's algorithm who breaks it down and rebuilds it using hypothesis tests and conducts statistical inference. So rather than going by some criteria of prediction accuracy, like mean square error or R-squared that you will be familiar with, we actually build this algorithm using hypothesis tests and statistical inference. Okay? Because at the end of the day, in econometrics, that's our goal. So I'm going to use inference-based recursive partitioning. It's called recursive partitioning because it repeatedly partitions the data. It repeatedly slices the data, okay, to identify these circumstance profiles. And by doing that, I'm going to measure the extent of this heterogeneity in that elasticity, which is intergenerational transmission of health. Okay. Now, in this paper, I conduct this exercise twice. I first build these inference-based, machine learning algorithms, inference-based trees. Okay, I'll show you what they look like. First, with a set of circumstance profiles. Okay, because I want to identify these types of individuals. And then once I've identified that, within the circumstance profiles, I'll fit another tree, this time using only the policy variables, like antenatal care variables. Because the second order question here is, for given circumstance profiles, how does the intergenerational transmission of health change by receipt or non-receipt of a antenatal policy? Okay, for a given circumstance profile. Okay, so should we get started?
So, how is methodology different from reinforcement learning that is often used?
Reinforcement learning. It's very different. Reinforcement learning it has a cost and a reward associated with it. Okay, so if the algorithm makes a mistake, you put a penalty. And if the algorithm, and using that penalty, you make it learn further. So it's an iterative algorithm that, there's a cost and penalty associated with it. This is nothing like that. So if you're aware of what a decision tree looks like, this is going to use a decision tree. We are going to change the splitting rules. We're going to change the way a decision tree is built. Okay. So how does machine learning help? And I'll spend a little bit of time on this, but if the audience is clear about this, we can move on to the actual results. So I use this, and it's called a model-based recursive partitioning, or rather MOP, to identify the circumstance profiles in a data-driven manner. Okay. And what do they do? So let me see if there's a So if you're familiar with prediction decision trees, okay, they split the data into subgroups using a prediction error minimization criteria. So can I use this? So in a sort of typical machine learning algorithm, you'll find that if you're familiar with trees, it will build trees like this. Okay. And each of these areas, there are some observations that are in these areas. So the model has partitioned the data into 4 parts. Okay. This is a hypothetical tree. Not all trees have to look like this, but something along this line, right? So we take this some variable x, say x1, and the model is going to decide at what value of x1, say some value s1, we're going to split the data set into parts. If x1 is less than or equal to s1, all the observations go along this branch. If the value of x1 is greater than s1, all the observations will go along this branch. Okay. Now, in a typical decision tree, how this is built is, there's a splitting rule that tells you what this x1 is going to be and what the value of s1 is going to split at. And that typical decision rule uses some, like I said, prediction error minimization criteria. So it could be something like mean square error, R square, something like that. Here, we are going to change this. We are going to use a rule that uses hypothesis tests. Okay. So that is what model-based recursive partitioning does. It takes hypothesis tests and statistical inference. Now, how is this an improvement? It's this middle ground between estimating your model in a fully parametric manner versus estimating your model in a fully non-parametric manner. Okay, so somewhere in the middle. So we have this sort of global model that I'll show that is in our head, which we take from our econometric knowledge. And instead of just fully using a non-parametric method, which is something like a traditional decision tree does, which doesn't matter what your model is, it will just look for those corners of the data where prediction error is minimized. Okay, instead of doing that, we are going to take the model and we are going to split the data set based on our model, conducting statistical tests along the way. Yeah, so a little bit of more about this, combining a fully data-driven approach to a fully parametric approach. Okay. Another way of showing you what the difference is, if you were using a traditional decision tree, like this one, the decision tree would split the data into different regions based on the value of the dependent variable, the value of the y. Okay. Here we are creating the tree with finding different regions of the data based on different patterns of association between x and y. Okay, so if you have some linear regression in your mind, a decision tree would give you some, the blocks of data where every block would have a different predicted value of the y. Here, we are going to partition the data into different blocks where every block will have a different value of a beta hat. So that would be a nice way of understanding the difference. Yes. Yes, we will talk about the splitting rule. That's exactly what the splitting rule tells us. Okay, and we will build that using hypothesis tests.
By definition, treatment effects of heterogeneous.
Yes, but I won't use the word treatment effect because it's not a causal work. Yeah. I'm going to look at by definition they're heterogeneous. Yeah. That's why it says heterogeneity in intergenerational transmission. So it's basically uncovering that heterogeneity. That's the task.
So the piece of the box that beta hat is different. How is it make a connection? But I say very different level. Also improving data.
Yes. The difference is you would a traditional decision tree, you wouldn't build it with testing for beta hat along the way. You build it by testing for difference in y hat along the way. Yeah. So we are not, so it's not like we are doing something else here. We are just building a different tree starting from scratch. Okay. All right. So showing you the main global model which we will start with. So if we want to do this in the traditional manner, we would fit a parametric model to the entire data set, right? And in the literature, you will find that this is the intergenerational transmission of health. Okay, so how much of the mother's health is passed on to the child. Okay, and X is a vector. It's the set of circumstances. So we are going to. This is our main parametric model. Okay, we will test for parameter instability over the set of circumstances, and that is the test that's going to give us this. Okay. So is there a natural breakpoint in the way other characteristics affect, the birth weight? Okay, and then within that we are going to find out these this elasticity of intergenerational transmission. Okay.
Traditional setup that amounts to interacting X with mothers.
Yes, in a traditional setup it would amount to that, but the difference in the traditional setup is that we choose the X, right? And there's also another issue. You can interact one or two at a time. After that, you fall into this problem of high dimensional problem, right? So there's too many interactions.
Simple question. There you're using mother BMI. Why particular BMI is that representing the health?
Yes. Mother's BMI represents the contemporaneous transmission of mother's health to the child. So mother's BMI at the time of pregnancy, at the time of birth. I also do another set where I use mother's height. So these have two different meanings in the literature. Mother's BMI gives you the short run health of the mother and the child, short run health of the mother, and that beta 1 will capture, as I said, contemporaneous correlation. Mother's height is considered a long run indicator of mother's health, and looking at that gives me the long run effect of mother's health on the child. Okay. So we here use just within 1 year of birth, so that there is yes, because I use the NFHS data and you can only get it after birth from the birth history file. So we just restrict to the first year after birth, those individuals who've been surveyed with the first year after birth, so that there's less recall bias and of course less chances of mother's BMI not being representative of what it was during pregnancy. Yes, but there's no way of measuring that. The way most health data sets are collected, there's no way of actually getting at the time of pregnancy. And this is sort of a comment on how data is collected in India. In other countries, this type of work is done with hospital records, where you have the mother's weight from or mother's BMI from doctors checking up on mothers during pregnancy, and then you can correlate it with birth weight at the time of birth. We don't have such rich data in India, so we have to make do with whatever is the second best. So I'll talk about the method by which we are actually, the statistical test, but this is quite a large literature, and I'm actually just using this from a particular paper. So, the underlying business theory of how to build these types of splitting rules, they use a kind of estimators in econometrics which we call N estimators. So these are essentially estimators which do not have an algebraic formulation, so we have to rely on an empirical nature. Okay, so some of you might be familiar with this from the time series literature, where there is the structural break tests. Yes, so we do something very similar to that. Basically, the test looks for structural breaks along this data hat for every individual X, which we call the circumstance. Okay, so it goes through the range of values for every individual X, finds the one where there is a structural break, picks the one to use to make a stick here. Okay,
Structural break in the relationship between mothers.
This structural break in this.
Circumstances.
Exactly, how circumstances affect the birth. Yeah. Now, so we start with this hypothesis that there is no structural break. Okay, so that's the null, and we go through each of the values of X to find the covariate for which there is a systemic change in the relationship between the beta. And so for all the asymptotic and theoretical results, I will refer you to this Z-Liss's paper, which has developed an underlying theory for this. So all this particular type of machine learning algorithm is doing is taking a kind of hypothesis test that already exists in the econometrics literature and plugging it into what is a traditional machine learning model and building something that is more suited for econometric analysis. So let me just go ahead and show you what I do finally. So once we build a tree using that structural break test, in each of these terminal leaves, we fit in this model, which is just estimating the intergenerational transmission of health. So the TLDR version of all of this is very simple. Build a tree using the circumstance, estimate intergenerational transmission of health in each leaf using our linear model, which we have from econometrics. Okay?
For each circumstance,
For each circumstance profile, I won't say circumstance profile, because we get it from like this could be one x1, another x2, all of that. For each of these, I am fitting this model.
for each of them,
There will be a different beta 1.
different data,
Yeah, I'll talk about that. Okay. So the goal, first of all, is to uncover the different beta 1s in a data-driven manner, right? We don't want sort of researcher bias, researcher to specify what these circumstances are going to be. Okay. You'll find some interesting things that show up once we do not tell the model what to look for. Yes, one model for each. Okay. You can, but so you have, like as a researcher, you have that freedom, but you should have a very solid reason as to why you're fitting different models in each state. So one of the reasons I fit the same model is because I want to then compare them and actually see the extent of heterogeneity. There are conduct some more statistical tests on them. So it has to be the same model.
In a way, clustering the data on the basis of common covariate characteristics, common circumstances characteristics, right?
They won't be common across the different circumstance profiles.
So given the circumstance profile, they are computed on the basis of beta 2, how whether there is a structural break in beta 2 for different values of xi's, right?
Yes, different values of xi's, yes.
So if I use simple clustering, A means clustering for different xi's, group the population accordingly, the samples accordingly, and then run the regression on different clusters. So how is
it's
that?
not the same thing. Clustering, the algorithm itself functions on looking for groups that are different in just the y, not the relationship between the x and y. Think about K-means clustering. It's an unsupervised tool. Okay. All it does is you tell clustering, you tell the K-means clustering algorithm what is that variable that you want, and it's going to cluster on the basis of this. Not a relationship between one variable and another variable.
What if I ask them to take an input of the covariate itself? So instead of considering y, I tell them to take xi's of all the outputs together 10%.
Then it will cluster on the basis of the values of xi, not the beta. This is the important thing to understand. All of this is dependent on the relationship between x and y. All of these traditional machine learning algorithms focus on the value of the variable itself, not their association. Okay. Okay, so we'll start with so let me give you an overview of what I do with the data, and then we'll start with the global model. So I use unit level NFHS 5, the most recent one. As I already answered, since I'm focusing on intergenerational transmission at birth, okay, I'm just, for this purpose, I'm just looking at infants who were surveyed within a year of birth, so that there's less recall bias and less chances of the mother's BMI being very different from what it was around the time of pregnancy. So that could be, you could tell me that maybe I should look at it more closer to the date, maybe 6 months or something. We could do some sort of robustness based on that. And so that leaves us with around 37,000 observations of infant and mothers. And so I take all of these characteristics and I divided them into two parts. One is the set of characteristics which we think are circumstances, right? Socioeconomic characteristics over which the baby has no control. like the religion, caste, location, income, wealth of the family, household size, mother's education and age, and so on. And then there's a set of characteristics which the mother has some control, but of course we know that it also is affected by circumstances. These are the extent of the different kinds of healthcare that the mother can receive. So antenatal visits, type of healthcare worker, which tells me the skill set of the healthcare worker, different kinds of injections, whether they're informed about potential complications, supplementary food, and so on. So there's actually a very small number of such the policy variables that are actually that have good coverage in the NFHS data. So we just sort of stick to that. Okay. So we start with two measures of mother's health, as I said, because we want to look at not just the flow and the stock measure. So with not just one measure, so we want to look at a flow measure as well as a stock measure. So BMI, which varies a lot around pregnancy, allows me to focus on the contemporaneous transmission, and height, which is a stock measure of mother's health. It allows me to look at the intergenerational transmission of long run health of the mother to the child. For infant's health, I look at birth weight. If you look at the literature, you'll find that it's often considered the first sort of stock of health that we inherit from our parents. And then there is a large literature that shows that birth weight has very enduring effects on education, adult health outcomes, disability, lifetime earnings, and a lot of other things. Okay, so we'll run a global model first to set the benchmark. Okay. And the first sort of model that I showed you, where we just introduce all of the circumstances linearly, the way we would do in a traditional econometric model. And this is just to set the benchmark for the estimates. So, for height, we get something around 0.42, 0.419. And so the first specification has just the socioeconomic controls, which are my circumstances. And I also include both the set of socioeconomic and policy controls to set the benchmark. Okay, so this is for the height, and these estimates are for the BMI. Okay. So now we will run machine learning on this and see how it gets what happens. So this is the first set of machine learning, the tree that we get. If I click outside, can you see the? No. I want this. The last row is not. Okay, fine. As long as you can see the numbers, the last row is just I characterized each of these types with a letter. Like I call them A, B. Yeah. So just call them type A, type B, and all of that. So what we get is when we first run this model-based recursive partitioning using just the circumstance profiles, the biggest sort of parameter instability comes from the religion. Okay, so it turns out that Hindus and Muslims and all other religions, they have the first break, so to speak, in terms of the parameters. Okay. Moving forward, mother's education provides a second break at like 8 years of age. So mothers who have less than or equal to 8 years of age, and then mothers who have more than 8 years of education are the first big split. For those who have less than 8 years of education, the gender of the child is the next big structural break. Okay. For boys, the intergenerational transmission is around 0.14. For girls, we see that there's another structural break which comes from the relative wealth of the household. So households who have whose wealth is in the first and second quintile, for them the intergenerational transmission is 0.15. For those who are a little bit richer, second, third, and fourth quintile, third, fourth, and fifth quintile, for them it is 0.11. So there's already a difference between worth of households for the same circumstance profile compared to the slightly better off households, right? So this is one second. So this is for the same circumstance profile. So in Hindus and Hindu-Muslim households with mothers that have less than 8 years of education, girls, for those who are within slightly poorer, have a larger rate of transmission compared to those who are slightly better off.
So I just wanted, from the technical side, from there to the more heuristic that you mentioned about the religion bit. What does that translate into the structural way that you're talking about? Is it, what you're capturing, assuming that everything is okay? Are these correlated with something else because of which this is happening? Yes. I don't know. I mean, you are taking the religion, for instance, as an important determining factor.
Circumstance factor. I wouldn't say intervening factor because
circumstance factor. For instance, you're saying that this group is more educated or less educated, has an opportunity of social mobility of this and that, the other, or their rituals. What is it that it might be capturing? I mean, just to start with that, things are wealth and other factors are, probably.
So I want to make a very important point here. This is not a causal analysis.
This is not.
This is not causal.
Oh.
Okay. It is documenting the extent of heterogeneity in the data-driven manner. So we are not saying that it's the religion that's causing this.
No, it's not an emotional factor. Yeah, I just wanted, as we go along, because said I can ask, just asking what is the heuristic of this? I mean, I'm not looking at it.
What we should take away from this is, in Hindu and Muslim households, the extent of intergenerational transmission is distinctly different from those in the other households. That's all.
The reason I'm asking this in the context.
This is not giving us a reason. And I'm not looking for the reason. It's about documenting.
Causal.
Yeah.
I'm intrigued by the fact that in India, you're looking at the Indian rate, right? If you exclude the Hindus and Muslims, the rest are very small and relatively insignificant.
Yeah. So that could be, that is a valid question. And so for a while, I thought that this is probably being driven by the data size. Not quite. So even in like the other sort of other groups, there's still a substantial number. So it's not a very small number. Okay. Secondly, this is, so I've done a bunch of robustness checks along like different resampled versions of the data, and this is an enduring result. It is the first big break that shows up. And if you see the literature, you will find that there is always a lot of discussion about this, that these religion has a role to play in how much of different health outcomes to begin with. And I'm looking at the extent of transmission of health. So it only makes sense that what we see as difference in health outcomes also stem over across generations. It also shows up in transmission of health.
You see, the reason is, for instance, rest of India is very clear cut. The religious divisions and all that. If you go to a place like Kerala, these are things that intriguing me. It's kind of equally divided, not quite equally divided. Very substantial portions of all three religions. But their underlying factors are those are also people in Kerala socially a lot more advanced, including educationally advanced.
So, one would have to look at this at a very state level in order to sort of look at your hypothesis. But unfortunately, in NFHs, we do not have enough sample size at the state level to conduct this analysis. We have to stick to the national level. So, first off here, we can see an evidence of how like socioeconomic characteristics is actually affecting, and then you basically see very clearly that work off within the same circumstance profile one particular characteristic, just the wealth of the household is giving you quite a bit of difference in the. Yes, so I'm coming to that. Yes, that's a very good question. We'll actually test this. We'll reverse engineer these same estimates and test for statistical significance. Within mothers who have more than 8 years of education, okay. So for boys, you see intergenerational transmission of 0.13. For girls, again, there's another further break depending upon the wealth of the household. And again, like poorer households have a much larger coefficient than relatively better households. Okay. So one thing you get from here is, first of all, wealth seems to matter for girls, not for boys. Right? Different levels of wealth. Exactly. Different levels of wealth. They seem to matter for girls, not boys. Another interesting thing that I sort of saw, and every time I ran this, and perhaps some of you could also shed light on this, that the break for the education of the mother keeps happening every time at 8 years of schooling. Okay? So my sort of working hypothesis is that it's because there are a lot of policies in India that also stop around that time. Right, so like I think for a long time midday meals used to be up to 8th grade, party exactly. So there seems to be a big break that's happening, structurally at 8 years of education for mothers. That seems to be.
That is elementary education. That phase is elementary.
Yeah.
So there you get the data. After that, it's a different.
No, the data set is the same.
No. But I'm saying a lot of things, policy continuity goes on.
Yes, there is a policy break. Like there are other things that are also stopping around that same time. And so it does show up. And this is one of those enduring breaks that actually showed up across like different robustness checks that we ran.
That is the elementary.
I have about 15 minutes. Okay, I better move fast then. Okay, so this is just summarizing sort of the difference in the elasticity of transmission of health, relative ranking. So comparing the estimates, so the red line is the estimate that we got from the global model. So I wanted to see exactly, does it make sense to fit a global model, or do we really should be looking at different models for different circumstance profiles? Okay, and you see that for some of them, your global estimate does lie within the confidence interval, but there are some groups for which they're absolutely outside. Okay. So it's not, fitting a global model doesn't seem to actually work for everyone.
Just this one, right?
Yeah, just what that. So this is, I'll go back to, this is type E, and that would be girls in Hindu or Muslim households with less than 8 years of schooling and relatively poorer. So, and to answer Bharti's question, so I thought that, we are using machine learning to get these different circumstance profiles, and we are getting different intergenerational transmission of health. But as economists, our next question is, well, are these statistically significant at all?
Okay, quick question. Sometimes you will find age at marriage to be significant. This age at marriage or age at birth, because that will explain your 8 years. People who study for 8 years have a later age at marriage. So that tells you.
I do have age at birth. I don't have age at marriage.
So because that information is there,
yes.
generally people will show that these two
are, but they're also like very highly correlated. You can ideally have any one of those in the model. So I did put age at birth. That wasn't one of the big things.
Because the second child of that age at marriage matters. Because you've just taken only the key. Anyway, that's the thought.
Yeah, no, that's a very interesting point. Okay, I'll look into it. So, now we have to test for statistical significance across these groups. Now, we built a tree by partitioning the data. So we have different chops and blocks of data. So now that we've uncovered the tree, we can reverse engineer the same estimates by strategically defining dummy variables. So we can define a dummy for leaf placement. Okay, and so we reverse engineer this tree get one regression equation. The first thing we do is check for overall significance, right? They are statistically significant, all of them. Then we check for, so we want to know, okay, they're overall different, but are they different from each other? So we conduct a series of pairwise tests, t-tests. And so this is what we find. So there are some groups that are very distinctly different from each other. So, so this is like a 2x2, which tells you which ones are significantly different from each other. So girls born in Hindu-Muslim households with slightly more educated mothers and better off, this is type F, are distinctly different from similar girls in relatively worse off households. So what I said earlier, that relative wealth seems to matter for girls, not so much for boys. That also holds true when we are doing this pairwise statistical significance. Similarly, for the same is for type B and similar boys, and then type A and type B, which are like, difference between them is just mothers with less years of schooling. So there is some distinct difference in terms of some of these groups. So now that we've done the main tree, where we've found this, how we've actually characterized the circumstance profiles, we'll, so I'll skip this in the interest of time, but I do the same thing with height, and overall there are very similar results. Here actually, age of the mother at birth actually shows up when it comes to height. And we find there's a distinct structural break at 24 years. Okay. Right. So we've done the first set, which is looking for circumstances. Now we are going to take each of these leaps, so each of these types, A, B, C, D that we characterized, and fit up another model-based recursive partitioning, but this time we're only going to use the policy gradients. And see now how much does this circumstance, this intergenerational transmission change by receiving or not receiving a certain kind of antenatal care. So the first type A, so these are based on certain types. Okay, then we see that those who are receiving care from, either they don't get any care or they receive care from community health workers. So those that don't get any care have a slightly higher rate of transmission compared to those that get care from community health workers.
Now you identify rates based on these policies.
Based on these policies, within a circumstance profile.
These policies are not strictly
No. That's why I said again, this is not, I will not interpret these as causal, because for that you have to find exogeneity. This is again just looking, basically, the goal is to see that is this extent of intergenerational transmission at all tempered by receiving antenatal care. Are we at all affecting that, that extent of sort of perpetuation of bad health in any way? So again, like not getting any care makes you inherit your mother's bad health a lot more. You have a higher elasticity of transmission of health.
You're making the statement, this makes it possible, right?
No, I'm just talking about association. So for these people who are not getting care,
selected set of people chose to get, antenatal care. So that's why I'm saying the moment you make this statement, sort of becomes possible.
So we don't know if they chose to get it or if these people didn't get it because they didn't have access to it. Right, because we just, in the data, we just observed that they did get care from community health workers. Right, that's how the question is asked, like, did you get, So that's all. So just the difference. Similarly, for those who did get care, the next break that the algorithm identifies is the number of antenatal visits. And for the ones who have, less than the required number of visits, so one here is, did they get 4 visits, which was mandated by WHO at the time of collecting this data? For them, in that subset of individuals, the elasticity of transmission is 0.16. for the subset of individuals who get more than the required number of care, for them the elasticity of transmission is 0.18. So there is a sort of higher transmission of intergenerational health in the subgroup that actually gets a lot more care. And for this, my working theory is that these are probably individuals who are already suffering from some complications, or they are like high risk or something, because they are getting, this is the group of people who are getting more than the number of visits that WHO requires. So probably there's some extra health concerns happening there. Okay, so I will just talk about similar sort of results that we see for some of the groups, and for some of the groups we actually don't see any more breaks, which means that there isn't a big structural break in that intergenerational transmission caused by any of these antenatal care variables, any of the policy variables. So they're not making any difference within that particular circumstance profile. For another group, we have the whether the mothers were aware of pregnancy complications, and the ones who were unaware. Of course, for that subgroup, there's a higher rate of transmission than any of the two subgroups where mothers were aware. And similarly, we see a similar effect with the number of antenatal visits. So I will just wrap up. So we have similar results for 2 or 3 other subgroups. And so, if you were to sort of summarize what each of these trees tell us, one of the results that stands out is that worse off circumstance profiles, if you look at those subgroups, they all have higher rates of this intergenerational transmission if you compare it to better off profiles. Relative wealth seems to matter for girls, not for boys. And within each circumstance profile, for some of the specific, getting antenatal care, for some of those is associated with slightly lower rates of intergenerational transmission than non-receipt of these. Most of them are not, so some of these subgroup estimates are not statistically significant, but some are. So essentially, what this is telling us is like fitting a global model for the entire data is not going to capture all of these non-linearities that exist, and identifying these circumstance profiles. Basically, they're telling you that different circumstance profiles have different rates of transmission of health from mother to child. So it's very useful for precision policy making. If we were to make targeted policies, then it's important to know how to target, right? And so this kind of an approach will actually tell you exactly what those circumstance profiles are and how to target. So I'll stop here and yeah. Thank you so much. Yes.
So here we are in a way talking about varying coefficient for different kind of circumstances. So in this case, how the results are differing if I consider it as a global model with a varying coefficient like generalizability. So how are the results differing in that case? Because as far as my thinking is, this might be computationally much more expensive compared to if I just go for a global model with a varying coefficient.
So you would run into the same problem that you would if you were trying to do this parametrically. So as a researcher, you are deciding what that X will be, and I mean you have to specify the number of interactions. So you would first run into the high dimensional problem that we face when we run any parametric model. You can only look at a few interactions at a time. So while this algorithm is being built, okay, which is what the test does, it considers all possible X and all possible values of S at the same time, and it picks the one that has the highest probability, like has the highest difference.
Simplest negative models, so the non-linearity of the coefficient, the varying coefficient, is itself defined by the data rather than we giving any parameters.
Yes, but if you were to do that, like if you were to try to find this, So couple of things actually. GAN will give you a series of betas for different values, right? Not a split point. So the first disadvantage you have is like where do you split? If you're getting a series of estimates, right? So you can think of this in a way that this algorithm is mimicking what a GAN would do, estimating a series of these betas and picking the one that there is a break and slicing the data there. Okay, so in a way, it's building on top of a GAN.
So there's one paper that I came across recently which talks about how GANs can be used for causal analysis.
Yeah, they can.
In that case, even this, if you're saying that it's built up upon.
So causal, see, the causality has to part come from exogenous variation. The model doesn't give you that, right? Like the functional form is not going to give me causality. Again, if I don't know which paper or what, but GANs can be used for causal analysis, assuming you have exogenous variation. Then what GAN will tell you is where's the extent of the heterogeneity. Okay. So the same is the true here, except we are interested in not only getting a series of betas, but we also want subgroups of the population. And it's telling me what those subgroups should be that have distinctly different betas.
So you're choosing this vector X, right?
Yes. Yes.
And then essentially identifying the cutoffs, the breaks.
Yes.
So the decision policy maybe to work best. You believe it starts with the maximum.
Right. That is the.
Chandra is saying that you add even that variable.
Yes. So here you have to use your judgment somewhat because adding like showing the entire bucket of all possible variables makes the algorithm, any machine learning algorithm, sometimes pick up noise rather than signal.
There's some.
Yes, it doesn't necessarily. So you have to start with a set of X that has some theoretical, theoretical backbone in the literature. Right? So what Chandra is saying, age of marriage is something with theoretical backbone, and I will consider it. I actually put in age at birth, and the two are very highly correlated.
The model can choose to discard it.
Yes, the model can choose to discard it. Yes, but it's not a prudent idea to dump everything in the model. Because then the model becomes computationally very, very slow. But the bigger problem is, see, the model does not know the theory. You know the theory. So the bigger problem is that the model often picks up noise rather than signal. There could be parameter instability from variables that genuinely don't have any intuitive reason why it exists.
Yeah, that's true when we're doing environmental analysis, right?
Exactly.
It doesn't make sense. I mean, you can keep putting in one of the variables to see.
Exactly, to see what works. And sometimes you pick up something that makes no sense, but it's just statistically significant. That is the same logic. So I don't recommend doing that. Yeah.
But I'm sorry I'm explaining this earlier, but how exactly is the split happening in each tell that?
So the theory of the test or?
Yeah.
So essentially we calculate code. Okay. Let me I skipped over the theory.
Just to ask, you're talking about two things where generally that's how it's done.
So
given the two variants, how exactly it's done.
So are you talking about like the traditional decision tree or this decision tree?
Yeah, how is it different?
So a traditional decision tree, when you're building the tree, you have to make a decision at every node. Which X to split by and which S to use. S is the value of that X. Okay? The way traditional decision tree does, they do it is they take all possible X and S combinations. Okay? Calculate the RSS here. Okay? Then take one X and one S, split the data, calculate the RSS here. Okay? This needs to be lower than this. Only then it means that the x splitting through the x has made this more pure. Or in other words, it is explaining the y. Now, in order to do this, it will take all possible combinations of x and s, do this, and pick the combination that gives the highest reduction. Then you have two nodes. Here, it will do the same thing again, and go on. Okay? So the entire tree is being built with the philosophy of prediction error minimization. Now, if you read the machine learning literature, you'll see that there are some issues with this. It tends to favor continuous covariance more than binary covariance. They tend to be picked more often. There are some other issues. Now, there's no reason, because we are not interested in predicting birth weight, right? If I was interested in predicting birth weight, this is the tree that I would use. But I am interested in looking for subgroups of the population where there is a difference in that data. So now we change this. Okay, we are not going to use this RSS. What we do is, this is a test that looks at something called an N estimator. So I'll tell you this, connect this with what we already know. So for example, if you were running a linear regression, this would be the RSS. Okay? Now, what it does is, you calculate the RSS at this node, okay? Then you basically calculate each observation's contribution to that. So, if you are running a linear regression, that would be the residual. Every observation's contribution to the residual sum of squares is that residual, okay? So you take, for example, you take 1x, take every observation, calculate its residual, order the x, order your observations according to the value of x. Okay, for example, if you have mother's age and you have like 18 to 54 in the data, first observation may not be 18. First observation's value might be 25 or something else. You reorder your data. Okay, 18 to all the way to 25 or 54, whatever I have. Okay, and associated with every observation, you have their residuals. Somewhere there will be a break. That is the value of x and s where you split it. Okay. Now this is for 1x. The test will conduct this for all of the x's and pick the one where that is the most. The break is the most biggest.
The regression in a case of running is being at the end of each node what you're running. It is weight and BMI and other variables at each node.
No, at each node what I'm running is this. At each node I'm running this and this.
All
of the x, all the circumstances. Yes, all the circumstances. And because it has to pick from that circumstance, which one is giving that structural break?
Just I think how the people talking about it, you use k-means clustering and cluster them, but you can use only a single series to do that.
No, you can, it doesn't have to be single value, it can be a combination of value, but k-means clustering will cluster based on the value of x, not beta, or value of y, not beta.
What if you do this one, say, let's say you run a simple regression of birth weight on BMI, and then do the clustering based on the errors, and then study the characteristics of each cluster. I'm not saying that's the right, I'm just saying.
So you are doing, by doing that, you are basically finding subgroups where of the unexplained part of the model. Like you're basically finding subgroups by what BMI doesn't explain.
With all the controls, you can see error, and then you classify it. And within those clusters, you look at the characteristics. Are there some common characteristics within each cluster?
I'm not following what you're saying. Like, are you saying that I run this regression and I cluster based on the epsilon?
So you have this regression clustering based on based on the error. So now let's say we have 3 different clusters. In each cluster, you will get there's a set of characteristics which you're looking at.
So first of all, it doesn't. Does make sense. So if I'm clustering with errors, that means I'm looking for subgroups based on unexplained characteristics. But I want to. Why would I want unexplained characteristics? Whatever is unexplained, whatever is the error.
This.
Yeah. Not. I don't think that. Yeah. Okay. Yeah. Not here. Maybe there's a better way to do it, but doesn't make very sense here. Yeah.
Instead of mentioning we are not independently causal effect, we are more interested in testing it. So our testing for whatever we have got, security decision has a history of overfitting. How are we checking for it? The level that we have got is actually use the ADS and not use some other function.
Right. So that's a very good question. And the thing is, with this type of tree, there isn't a lot of available tests for cross validation. So we have to do our own thing. So I follow the philosophy of machine learning, where I create bootstrap resamples and run the similar thing to check we get very similar trees. I also divide the data into training and test. The way we do it in machine learning, 60-40 or 70-30 kind of a split. Build on the training data, test on the test data, and see how well the model fits. Okay.
I run a formal testing tree and I get the load splits. Somehow I get a very comprehensive tree because avoiding overfitting and I get some comprehensive splits. And I fit it parametrically with my data to avoid not being, suppose I'm not able to estimate a leak because I have very less because we are fitting multiple. Suppose I just use the decision tree to get some splits and then fit it parametrically with the interactions.
So fit the regression in the leaf.
So I'll only get the subgroups. I don't want the splits.
Right.
So I don't like get in the channels, right? So for me,
so this is the thing. If you fit it using prediction error minimization criteria, we are not getting the same tree. It's not building the same tree. A decision tree will be a traditional decision tree is built based on, and I talked about this at the beginning, where the Y is different. So if you know the way the algorithm works, it does not look at associations at all.
So if your X split is based on the difference in the
beta. Everywhere the split is being made based on beta. Where beta is changing, that's where the split is being made.
But your tree want to say that value of X where the beta one will be different. That's what eventually you're testing.
The X circumstances, no. The split is based on these betas. And in each leaf, we are estimating this beta.
And then to go and check whether the betas across beta ones across.
Yes, whether beta ones across each of those leaves are statistically different or not.
But if I get a decision tree, get the splits and I fit the parametrics, which is interacting my models BMI with that threshold of X.
A regular decision tree? Which decision tree? This is called a model-based decision tree because I'm starting with a model. See, a regular decision tree is not this. It's not going to give me the same tree. It's just not going to give me the same tree because the splitting rule is different. The philosophy of model fitting is different.
Normal decision tree is the value of X where the Y is different.
The normal decision tree will give you different splits based on the value of Y and Y alone. Where are the birth rates different? That's what a normal decision tree is.
This is primarily used for detecting heterogeneous effects.
Yes. If you're familiar with causal forest, it builds on this kind of a tree where we split not just using this M estimator that I said, but we split based on average treatment effect, where average treatment effect is different across each of the, because then you can interpret the data as average treatment effect. Thank you.
All right, thank you so much.
Thank you so much.